Imagine if buildings could repair their own cracks without human help. Sounds amazing, right? Scientists are studying a special bacterium called Sporosarcina pasteuria. This microorganism can produce calcium carbonate, a natural mineral similar to cement. They react with nutrient and calcium to form crystals that gradually fill the crack. This process called MICP. By helping concrete heal itself, this technology could create stronger and long-lasting buildings.
Sporosarcina pasteuria is a type of bacteria found in the soil, especially in alkaline places. It is special because it can break down urea into ammonia and carbonate. When calcium is present, these combine and form calcium carbonate, which is hard, cement-like material. This process is called MICP, microbially induced carbonate precipitation. In construction, this bacteria can be added into concrete or crack. When water enter, the bacteria become active and start producing mineral. These minerals slowly fill the crack and small hole in the concrete. This makes buildings stronger and more durable, and it also supports eco-friendly construction.
Before discussing its applications in construction, it is important to understand the characteristics of Sporosarcina pasteuria. Sporosarcina pasteuria is a gram-positive bacterium commonly found in soil. It is widely known for producing a large amount of an enzyme called urease, which plays a key role in biomineralization processes. Another important characteristic is that it is non-pathogenic, meaning it does not cause disease in humans and is considered safe for environmental and construction-related applications. In addition, Sporosarcina pasteuria can form endospores, allowing it to survive under harsh environmental conditions such as heat, dryness, and nutrient limitation. This ability increases its chances of remaining viable for long periods. The bacterium is also highly tolerant to alkaline environments. Since concrete typically has a pH between 12 to 13, this characteristic enables Sporosarcina pasteuria to survive and function effectively within concrete structures. Because of these unique characteristics, Sporosarcina pasteuria has become one of the most widely studied bacteria for sustainable construction technologies. Now that we understand the characteristic of Sporosarcina pasteuria, let's look at the process that makes this bacteria valuable in the construction industry. This process is known as microbially induced calcium carbonate precipitation, or MICP. MICP is a natural biological process in which microorganisms such as Sporosarcina pasteuria induce the formation of calcium carbonate crystals. Calcium carbonate, is also known as limestone, is the main mineral produced during this process. In MICP, Sporosarcina pasteuria produces an enzyme called urease, which breaks down urea and creates conditions that promote the formation of calcium carbonate. These calcium carbonate crystals can accumulate within pores and small cracks in construction materials. As a result, MICP can improve the strength, durability, and overall performance of structures. It can also reduce water penetration and help repair minor cracks in concrete. Due to these benefits, MICP has attracted significant attention as an environmentally friendly and sustainable technology for the built environment.
Sporosarcina pasteurii is a urease-producing bacterium that can promote the formation of calcium carbonate. The bacterium produces an enzyme called urease, which breaks down urea into ammonia and carbon dioxide. This reaction increases the pH of the environment, creating alkaline conditions that favor calcium carbonate precipitation. When calcium ions are present, they react with carbonate ions to form calcium carbonate crystals. These crystals fill cracks and pores in concrete, helping to improve its strength and durability. The self-healing ability of Sporosarcina pasteurii is based on a process called microbially-induced calcium carbonate precipitation, or MICP. In this process, the bacteria produce an enzyme known as urease. Urease breaks down urea into ammonia and carbon dioxide. The carbon dioxide then reacts with water to form carbonate ions. These carbonate ions combine with calcium ions to produce calcium carbonate, or CaCO3. The calcium carbonate acts as a natural cementing material that can help and seal cracks in concrete. To help visualize this chemical reaction, let's watch a short animation. As shown in the animation, the formation of calcium carbonate is the key step in the MIC process because it helps seal cracks and strengthen the concrete. Self-healing concrete is produced by incorporating Sporosarcina pasteurii bacteria and nutrients into the concrete mixture during production. When cracks develop and water enters the concrete, the dormant bacteria become active. The bacteria produce urease and initiate the MICP process, leading to the formation of calcium carbonate crystals. These crystals gradually fill and seal the cracks, reducing water penetration and preventing further deterioration. As a result, the concrete becomes more durable and requires less maintenance over time. To better understand this process, let's watch a short animation. As shown in the animation, the calcium carbonate crystals seal the cracks and improve the durability of the concrete structure.
When cracks form in concrete, the bacteria produce calcium carbonate crystals that fill and seal the cracks. This prevents the cracks from growing larger and causing further damage. As a result, the concrete remains stronger and more durable over time. Secondly, Sporosarcina pasteurii reduce water penetration and reinforcement corrosion. Normally, water and harmful chemicals can enter through cracks and reach the steel reinforcement inside the concrete. This causes corrosion and weakens the structure. However, when the cracks are sealed with calcium carbonate, water cannot easily enter, protecting the steel and maintaining the structural integrity of the building. Thirdly, the use of self-healing concrete helps lower maintenance and repair costs. Traditional repairs require workers, equipment, and construction materials, which can be expensive and time-consuming. With bacterial self-healing concrete, small cracks can repair automatically when water and activate the bacteria. Therefore, maintenance is needed less frequently, resulting in significant cost saving. The first application is self-healing concrete for buildings and bridges. The bacterial spores and nutrients are mixed into the concrete during construction. When cracks develop and water enter, the bacteria become active and produce calcium carbonate. This automatically seals the cracks and help maintain the strength and durability of the structure. Second application is crack repair in existing structure. The bacteria can be sprayed onto damaged surfaces or injected directly into cracks. Through the MICP process, calcium carbonate crystals form inside the cracks, sealing them and preventing further deterioration.
This method is considered environment friendly because it reduces the use of chemical repair materials. The third application is soil stabilization for foundation and slope. The calcium carbonate produced by the bacteria binds slope particles together, making the soil stronger and more stable. This helps reduce erosion, improve foundation support, and minimize the risk of landslide or ground failure.
There are several benefits of using Sporosarcina pasteuria in construction. First of all, it allows concrete to heal on its own, which can reduce the repair cost. Secondly, it can make buildings stronger and long-lasting by preventing water damage and rust in a steel. Thirdly, it is better for the environment because it can reduce the need to produce cement, which can create a lot of carbon dioxide. It can also help improve soil strength in construction area. Overall, it helps construction more suitable, strong, and cost efficient. I will explain about the limitation of Sporosarcina pasteuria. Even though this bacteria is useful, there are some challenges. First of all, it can be expensive to produce and use on a large scale. Second of all, the bacteria need certain conditions like water and nutrients to stay active. Without them, it cannot work well. Thirdly, long-term performance and in real building is still being studied. Also, it is difficult to control how the bacteria behave in a large structure, especially in a very hot and dry environment. So more research is still needed before it can be widely used in construction projects.
In conclusion, Sporosarcina pasteuria is a unique bacterium that has gained significant attention in the field of sustainable construction. Its ability to survive in harsh environments and produce urease makes it highly suitable for microbially induced calcium carbonate precipitation or MICP. Through this process, calcium carbonate is formed and deposited within construction materials, allowing cracks to be sealed and structural integrity to be improved. This mechanism has led to the development of self-healing concrete, which can enhance durability, reduce water infiltration, and extend the service life of infrastructure. The use of Sporosarcina pasteuria offers several benefits, including improved material performance and a more environmentally friendly approach to construction. However, limitations such as cost, large-scale implementation, and long-term effectiveness still need further investigations. Overall, Sporosarcina pasteuria demonstrates how microbiology can be integrated into engineering solutions, providing a promising pathway to a more resilient, innovative, and sustainable built environment in the future.